To Antarctica, so it's a real pleasure to host Dr. Will Hobbs today. He's an oceanographer, a meteorologist and a sea ice researcher who co-leads the Sea Ice Research Program, the Australian Antarctic Program Partnership. Dr. Will has spent 20 years studying Antarctic sea ice, and he's here to share what it is, why it matters, and why scientists are so concerned about the changes we've seen in recent years. Please join me in welcoming Dr. Will Hobbs.
Well, thank you everyone for coming on such a blustery day. Thanks to TMAG for hosting. I believe. How's that? Is that any better? No? All right, we can get rid of this one. How's that?
No good.
Yep.
I need the other one for sound.
Oh, okay. You're not going to get any problems with feedback? All right, great. My background, I'm a physical oceanographer at the Australian Antarctic Program Partnership based at the Institute for Marine and Antarctic Studies. I apologise for all the acronyms. Believe me, it is not what scientists would choose, but it is the way Antarctic research works at the moment in Australia. So, although I work as an oceanographer, as the introduction said, my background is actually meteorology. I only really pretend to be an oceanographer, but my main area of study is Antarctic sea ice, which is what I'm going to talk about today. Although my name is on the title, I should acknowledge that I'm going to give an overview of the work that we're doing at AAPP, and that includes a cast of thousands. I haven't really named anyone specifically, but be aware that this is not just my work. So it's always said that you should never start a public talk with a graph. But I'm going to, because I think this is my career, more or less. So basically what we're looking at here is the satellite record of Antarctic sea ice area. So basically if we take all the area of the Southern Ocean covered by that white stuff, sea ice, in that example map there, and with that we calculate the area in millions of kilometres squared, and that is one of our key indicators of the Antarctic climate system. And so the graph there is showing anomalies, so basically whether there's more ice or less ice than we would expect for any one month, going back to the late 1970s. And for the first part of my career, we were trying to explain this, let me see, can you see that? Yeah. Yep, this positive trend. Why was Antarctic sea ice stable or even increasing, despite the fact that the rest of the planet was unequivocally warming? Now, this was a matter that certain people who are less inclined to believe in the science of climate change really loved this record, but there were some very interesting reasons why, and that really dominated a lot of sea ice research for a long time. And then in late 2016, it would have been August 2016, after many years of work, I published this big, long, seminal review of all the reasons why Antarctic sea ice was increasing. A month later, it started collapsing. And then, for much of the subsequent years, we were trying to explain this collapse. Now, as you'll remember, late 2016, Donald Trump was running for president for the first time. And we thought this collapse was kind of the same. It was fascinating, kind of alarming, but there was no way it was going to hang around. Unfortunately, experts have been proven wrong on both counts. And as you can see, Antarctic sea ice, although it did briefly recover for a few years, it has stayed very, very low. Since 2016, almost every single summer, except one or maybe two, has been one of the lowest on record. So I'm going to talk about the work that we're doing trying to explain this sudden change and how we interpret that, and in particular, what does the near future look like. But before that, there's a very obvious question we need to ask, and that is, what is sea ice? Because we hear a lot about ice in Antarctica, but often there's some confusion over what it is. Now, I'm sure everybody has seen incredible photos of these vast, beautiful Antarctic ice formations. That is not sea ice. That's an iceberg. I don't care about icebergs. See the dull, flat scum in front that's really uninteresting? That's sea ice. That's what I'm interested. So sea ice is frozen seawater, and that makes it subtly different from anything else in Antarctica. So if you look at this schematic, this was published in a conversation piece. So Antarctica is made up of an ice sheet. So an ice sheet is basically, it's snow that has accumulated and never melted over hundreds and thousands of years. And that ice sheet is, when we talk about Antarctica's contribution to sea level rise, that's what we're worried about. It's moving that ice from land into the ocean, raising the sea level. Now, ice, as you know, I'm sure, flows down, and that ice sheet flows down towards the coast, and in many places it starts floating and becomes an ice shelf. Once it's an ice shelf, it is part of the sea level budget. This line here, we sometimes call it the grounding line. Once it crosses that line and starts melting, that's really the point at which it becomes part of the sea level budget. Now, an ice shelf has this cavity underneath, and this front here that we call the calving front is typically 300 to 600 meters deep. So it's pretty big. And we call it the calving front because that's where icebergs carve off. And you've seen icebergs, which I showed in the previous plot. Again, icebergs are pretty big, they're pretty deep. They can just slough off and be as thick as the ice shelf itself. Sea ice is much smaller. It's only a few meters thick. It's not hundreds of thousands of years old. It's typically a few months old. So it's not as impressive. But because it is frozen seawater, it's unique because it's salty. All that other ice is what we call meteoric ice. It's come from the sky. It's snow, meteorology. And it's mostly fresh. Sea ice is different. Now, I said earlier that it's not very spectacular to look at, and certainly that might be true on the deck of an icebreaker, but it has one thing that makes it amazing, which is if you look at it from a satellite, it's got this vast seasonal cycle. Every single year, an area 2.5 times the size of Australia freezes over in the Southern Ocean and then melts back in summer. And that's just business as usual. Think of that. It's like doubling the continent of Antarctica every single year and melting back. It is arguably the biggest seasonal cycle on the planet. People who study Arctic snowpack argue that theirs is bigger, but they're not here to defend themselves, so we'll call it. So that's what sea ice is. It's frozen seawater, and it's pretty ephemeral, at least in Antarctica. And why does it matter then? So I'm sure many of you will perhaps not have seen a projection of the planet looking like this. We've just generally seen a square map projection with either North America or Europe in the middle because, that's our post-colonial view of the world. But this is what's called a Spillhouse projection, and this is how oceanographers think of the world. So it's the three ocean basins which are connected around the Southern Ocean, which is one of the only place on the planet where the three major ocean basins can circle around and mix up, which is why the Southern Ocean and Antarctica are in the middle of this plot. But sea ice plays a really important role because if you have a look at that current system that is very simplified here, but you get the idea, where red are surface currents and blue are deep ocean currents, you can see a lot of sinking, a lot of connection between the surface and the deep ocean around Antarctica. And that's really important. Now, that seasonal cycle of sea ice is one of the important components of that connection between the surface and the deep ocean. Now, I told you that sea ice is salty, but when you freeze the seawater, about 2/3 of the salt gets purged out initially, and then it leaches out. We call this brine rejection. Now, in polar oceans, the dominant control on buoyancy, whether a parcel of water floats or sinks, isn't temperature, but salinity. So when you dump a lot of salt into the surface, that water gets heavier and it sinks. When the sea ice melts in spring and summer, of course it's fresh, and it places a nice fresh cap on the surface, at least over the summer. That pump of salt and fresh water helps drive that connection between the surface and the deep ocean. Now that's really interesting in its own right, particularly if you're a bit of a nerd like me, but it is important for you because the ocean absorbs 90% of all the heat that we're trapping on the planet and 43% of our CO2 emissions. And the Southern Ocean plays an outsized role. I think the Southern Ocean, at current estimate, absorbs about 16 to 20% of all our carbon dioxide emissions and 70% of all the heat that's being trapped. Without that surface, the planet, on the back of the envelope calculation, would be warming up at about 1 degree a decade. We would not be arguing over whether climate change is important. We'd already be dead. The planet would no longer be habitable. So that connection between the surface and deep ocean is key for setting how much climate change we get effectively, even here in Australia. The other thing you need to know about sea ice is that it's highly reflective, particularly to sunlight. Now in this image, you can't actually see any sea ice. What you're seeing there is snow on top of the sea ice. Of course, the sea ice provides a platform for the snow. And as I'm sure you're all aware, snow is very reflective and it bounces sunlight back into space, whereas the dark ocean will absorb that sunlight. Those of you who, like me, are a little follically challenged will know summer's coming and we've got to protect ourselves from the sun. The Southern Ocean is exactly the same. Now, the fancy term for that reflectivity is albedo. Some of you might have heard of something called the albedo feedback. Less sea ice means that the ocean absorbs more sunlight, it warms up, a warmer ocean has less sea ice, and so on. Now, we can tell in the last 10 years under a lower sea ice and lower Antarctic sea ice state, there is a measurable change in the Earth's energy balance. It's about 10% of the greenhouse gas emission effect just from that extra absorption of sunlight. But perhaps more importantly is where that sunlight is being absorbed around Antarctica. So I talked earlier about the difference between an ice sheet and an ice shelf. One thing I forgot to mention is that the ice shelves are really important for slowing down how quickly ice sheets fall into the ocean. So even though ice shelves are floating, they do slow down sea level rise. Now that loss of summer sea ice could be a problem for the thinning and the loss of those ice shelves. So we've got two things going on. In summer, sea ice loss means, like I said, you're absorbing more sunlight. That means that ocean around Antarctica's ice shelves warms up. Warmth is not very good for ice. Another aspect to this story that I don't have a cartoon for is the effect of waves. Sea ice, even though it's only a few meters thick, provides an important mechanism for damping the effect of ocean swells. Those ocean swells can flex an ice shelf and speed up calving rates. So the combination of warming and waves means that there is now, we published a paper earlier this year, there is an observable relationship between iceberg calving rates and loss of sea ice around Antarctica. Now, that idea around frontal melt, melt lots at the calving front, is relatively new. Most of the research in the last decade or two on ice shelf melt has been concerned with the basal melt, melting at the base of the ice shelf in this gap here that's called the ice shelf cavity. So we have warm, deep water. It's not actually that warm, it's about 0.5 degrees C, but if you're an ice shelf, that's pretty warm. Coming up from the deep ocean onto the continental shelf and melting the ice shelves underneath. But remember, I talked about that purging of salt when sea ice forms. In areas of very high sea ice production, you're creating this very, very cold water. It's about minus 1.8, which is the freezing temperature of typical Southern Ocean water, and creating all that salt. So you get this layer of dense cold water or dense shelf water, and that provides some protection for some ice shelves against the upwelling of that warm, deep water. It's one of the aspects why some ice shelves in Antarctica have retreated very, very rapidly, and others seem to be very, very stable. There are multiple aspects why, but sea ice is an important component of that, so it would be better if we didn't see too much loss of sea ice. So I've talked about physical impacts, but of course one thing that we think of when we think of Antarctica is that iconic ecosystem, and it's really an irreplaceable resource. Now, I showed images earlier of sea ice looking all pristine and snow-covered and sterile and beautiful. When you flip sea ice over, it looks like this. It's brown and green and disgusting. Well, not disgusting, not if you're a biology. Sea ice itself is an important part of this ecosystem that has developed over thousands of years, not just to tolerate sea ice, but to thrive on it. And so it's a habitat in its own right. Now, different species react to sea ice in very, very different ways, whether directly or indirectly. And so it's really complicated to say some simple summary about how the ecosystem as a whole responds to sea ice. But what I can do is what I thought it would be good to do is give just a couple of examples, two very different examples of two different species that are pretty prevalent in the Australian Antarctic sector. Of course, the iconic emperor penguin and the less iconic but infinitely more adorable Adelie penguin. And they react very differently. So first we'll talk about the emperor penguins. Now, emperor penguins have a very direct relation to sea ice, and in particular to what we call land-fast ice. Land-fast ice is the area of expertise of Alex, who's in the audience. Land-fast ice is ice that is stuck fast to the coast or to icebergs, and so it's not moving. And that means it's a very stable platform. And emperor penguins use that platform to raise their chicks. So you've seen, I'm sure, these photos of adorable emperor penguin chicks covered in their floofy down jackets. If you've ever got a down jacket wet, you'll know that they really need to stay out of the water. And so if that fast ice on which the colony is based breaks out and melts before they're fledged, before they have their feathers, before they can melt, which is typically mid to late December, I think. I'm not a penguin biologist, but it's around that time. If it breaks out too early, then that colony is done, complete breeding failure for that year. And in fact, this was measured, and some of you might have seen this news story, that was measured in real time or observed in real time by scientists using satellite data where they saw a colony. Actually, from a satellite, you can't see penguins, but you can see the penguin crap, basically. You can actually see that colony break out before the chicks have fledged. Complete breeding failure for that year. Now, these animals live in one of the most dynamic and harsh environments on the planet, and so that's not unusual for a colony. The problem is when it's happening to all the colonies year in, year out, and then it starts becoming a species problem. And then that map there shows the December, probably 2022, I can't remember, but I'd have to check. The magenta line shows where we'd normally see sea ice at that time of year, and you can see vast areas of the Antarctic coastline ice-free, implying no fast ice. Did the chicks fledge in time? I don't know, but this is one of the big problems. So, emperor penguins, very, very direct, relatively simple relationship. Adelie penguins have a slightly more complex relationship with sea ice. They don't like sea ice, or at least not in summer. They raise their young on dry land. They prefer not to have sea ice. Sea ice is just something that they have to walk over in order to get to their foraging grounds. And so if they've got a low sea ice year, they tend to actually do better because they're close to the land. But although the penguins themselves don't like the sea ice, they like krill. Now, not much is known about the winter cycle of krill, which is one of the keystone species of the Southern Ocean for many, many animals. But it is widely thought by krill biologists that sea ice over winter provides a critical habitat for juvenile krill. It gives them crevices and cracks from where they can hide from predators, and that green mucky stuff, all that algae on the underside, gives them something to graze on over winter. And so a loss of winter sea ice is bad news for the Adelies. And in fact, there are observations from Japanese colleagues of their emperor penguins. The Adelie colonies were doing really well in the late sort of teens because there was low summer sea ice and they liked that. But when we started losing winter ice, which I'll talk about later, they're not doing so well now. So these are actually observed relationships that we're seeing in real time. And that was kind of depressing, so let's move on. So should we care? Should we be worried? Is Antarctic sea ice changing? Well, I've already shown you this chart here, and you see that sudden big jump in 2016 and those low records. But what this graph doesn't show you, it shows that sudden jump, but what it doesn't tell you is something really remarkable happened in the last few years, because that graph doesn't really show you too much about the seasonality, which I think is the thing that has alarmed experts, and I flatter myself perhaps with that tag, that tells us something is really changing very rapidly. So let me go through this. This is from my colleague Ed Doddridge, whose name is on the board there actually. So this is exactly the same data, it's sea ice area anomalies, but it's chopped up into individual years. Every grey line is 1 year, and so the spread in those grey lines, the spread in that spaghetti, just tells you how much variability there is from 1 month to the next. It's interesting to note that March, April has significantly more variability than late winter, even though there's 8 times as much sea ice in late winter. Winter variability, whether it's that long-term trend or the recent extremes, generally is very, very muted for a number of reasons that I don't have time to go into. That's 2023. That's when we really sat up and took notice and started getting very worried. Now you can see that the magnitude of that anomaly, just how far outside of the norm it is incredibly remarkable. It's not just a record low, it's a record low by orders of magnitude. But also the time of year, the fact that we were losing ice in winter and not just summer when we're used to seeing big fluctuations, was I think the point at which we started realizing the system is perhaps changing. And sadly, that has continued. 2020, last year, was another very, very low year. This year wasn't as low, but let's face it, if we'd seen this year's record back in 2022, we'd be on the phone to the media. It's just an aspect that we think this is less bad, is really just a damning indictment of how rapidly things are changing. So one of the things our group has done with this, so I apologise for the pea blasting. One of the things we've been doing is looking into that and trying it from a statistical point of view and see were there any indicators, were there any signs, should we have seen this coming? And to do that, we've turned to an element, a mathematical theory called dynamical systems theory. Now, dynamical systems theory has been used in physics, ecosystems, epidemiology, climate science. Economists love it. So it's pretty widely used and it's pretty well proven. But dynamical systems theory suggests that there are some precursors, potential precursors to what they call an abrupt critical transition, which basically just means a sudden change. So I'm going to go through those. So the first one is an increased variance. So variance just means how much something fluctuates from 1 month or day or year to the next. So we've already seen a version of this plot. This is subtly different because I'm not showing sea ice area here, but I'm showing sea ice area normalized by standard deviation. If you know what standard deviation is, awesome. If you don't know what standard deviation is, don't worry about it. It's just a metric of variance. Anything within the 2 standard deviation range, the 2 horizontal dashed lines, we might consider business as usual. The odd flip over that line, that's just normal variability, nothing to see here. But if you look closely, as well as those changes in the mean state, the increase and the decrease, you can see that these fluctuations seem to start getting bigger and bigger and bigger. And those fluctuations are not just negative, they're positive as well. And in fact, that variance, that measure of variance, the standard deviation, has more than doubled before and after 2006. So long before we started seeing sudden changes. And so that is a pretty significant change in variability. So yeah, we definitely see an increase in variance. Another sign is an increase in autocorrelation. Now, autocorrelation is just a fancy statistical term for how much memory a system has. Or you might think of it, how long it takes for the system, after some anomaly or some hit, to revert back to normal. So if we think about just weather, if it was a cold day today, we might expect it to be more likely to be a cold day tomorrow rather than a hot day. I mean, obviously in Tasmania in spring, that's maybe not true. But for most things, most geophysical systems like the ocean, there is some memory in the system. Autocorrelation is just the statistical metric for that, so don't worry too much about it. So let's have a look at that record again. And you can see that before that 2006 change, yeah, you get anomalies, but they revert back to normal pretty quick. They're spikes. They revert back. Things start slowing down. We call this slowing down. They stay high, they stay low for a long time. It is developing some memory. It is developing some autocorrelation. And in fact, if you calculate the relationship between one summer, sea ice in one summer and sea ice in the next summer, before 2006, it was effectively zero. There was no relationship. I don't have time to explain why, but the system always resets in the winter. That is no longer the case. Now that R value, the highest value you can get is 1. So 0.61 in the game that I work in, that is a really high number and a very sudden change. So, increased variance and greater autocorrelation. This is what the mathematicians call the critical slowing down. And the third metric is increased spatial coherence. Now, spatial coherence in this example just means, are we losing ice everywhere? Is that a coherent response? Or do we lose ice in a few places and increase in other places? It's not very coherent. Let me just give you an example. So this is just a randomly chosen December with relatively low sea ice. Red means there was less sea ice, blue means there was more sea ice than usual, and you can see that that pattern overall is some red, some blue as well. It's not very spatially coherent. There's not one thing going on, there's a lot going on. If you have a look at December 22, it's basically all red. The only area that really isn't red is this area, the Bellingshausen Sea. That's not shaded because there was no sea ice that year. So that's a bit misleading. So that's what I mean. So it is definitely more coherent. One of the reasons why recent summers have been so low overall is because you are losing sea ice everywhere and not just a few areas. So that's what we mean by increased spatial coherence. So we've got 3 potential indicators of a coming abrupt critical transition going back at least 15 years. Has there been a regime shift? I'd say there probably has. And I'd say the indicator was there for a while, had we but seen it. So why is this happening? What's driving this? So this is my slightly flippant slide for what Antarctic sea ice research has looked like mostly in the last 2 decades. So what this is an example of some kind of sea ice anomaly where blue is less sea ice and red is more sea ice, and over the top are just wind vectors. And this is from one of my papers, and I actually can't remember whether this is a trend or an anomaly from a particular month, but this kind of plot is so ubiquitous. So what we can see here is that wind coming off the continent physically pushes the ice out. It's floating so it can move around, and because it's cold, the water behind the sea ice refreezes. So if you've got a northward wind coming off the continent, you will get you will get more sea ice. And the opposite is true in this direction. If you've got wind coming in from a lower latitude, it's bringing in warm air and it's pushing ice up against the continent. Just like in Tasmania, our weather is largely set by whether the wind is coming off the Australian continent or the Southern Ocean. And so because of that strong connection, basically Antarctic sea ice has been very slavish to the atmosphere, and Antarctic sea ice research has been very slavish to the atmospheric scientists. To give you another example, we've already seen this plot of sea ice area, and the black line is the observations that I've already shown you. The two coloured lines are from Australia's Ocean and Sea Ice Model, Access. Don't worry about the different colours. They're basically all the information that the model has been given is just the atmosphere. The two different colours are two different versions of the same atmosphere. So that's the only information the model has, and yet it is able to capture that variability in the satellite record incredibly well. And that's just an indicator of just how important the atmosphere is. Until we get to after 2016, and you can see those coloured lines start diverging a little. And I can highlight that just by calculating the bias. So basically, this is the difference between those coloured lines and the observations and the black line. And in that early part of the period, they sort of fluctuate around. No model is perfect. But we can see this ramp up of that error term, that bias. The key point here is that historically, sea ice variability in Antarctica has been almost exclusively down to atmospheric variability. That is no longer the case. We cannot explain the recent years from the atmosphere alone. And so if it's not the atmosphere that's driving sea ice, it has to be the ocean. Another graph, I apologise, but it's a good way of summarising a lot of data. So this is the record of ocean surface temperature in the Southern Ocean, again over a similar satellite period, and we can see after 2016 that big ramp up. The Southern Ocean has suddenly, after all those decades of being relatively stable and relatively unresponsive to climate change, apparently it suddenly seems to have caught up and is warming up. And we're pretty clear now that what we're seeing in terms of sea ice loss is related to this change in the ocean temperature. But we have a problem, which is we don't actually know where that heat is coming from. And that might sound like a slightly academic and abstract statement, but it does have some serious implications. So I showed that plot, the time record of ocean sea surface temperature, but if we have a look at the map, you can see that the Southern Ocean north of the ice edge has been getting very, very warm in those last decades, and often those red blobs do correspond with areas of ice loss. So the black line here is where we would have expected the sea ice edge to be at that time of year. For that year, 2023, this is where it's obvious where it was. Is it possible that ocean surface heat is now crossing that very complex current, the Antarctic circumpolar current, and affecting the sea ice? So if heat is moving southwards, whereas previously it had been somewhat protected. It could be a temporal thing. So I mentioned that we've had subsequent multiple low sea ice summers, and I also talked about that albedo feedback. So having all those low sea ice summers meant that the ocean was collecting more sunlight and warming up. Now historically, like I said, Generally, you'd expect the system to reset every winter, but perhaps having a warm summer after warm summer or warm summer, has the ocean accumulated enough heat that is now affecting the winter sea ice? It's possible. Or is it coming from the deep ocean? So we're looking here at ocean temperature for the Weddell Sea, which is one of the areas that was strongly affected. That's this region here. Kind of, you can think of it as the South Atlantic sector. Oh, excuse me. And we're looking at ocean temperature as a function of depth. And you can see this heat starting to accumulate below the surface at 100 meters and then beginning to pop up. So maybe this heat is coming up from below and the surface. Now, this question of where the heat is coming from has a really big implication for that big overall question, which is this an anthropogenic? Is this caused by human climate change, or will we see a recovery? Because if it is that surface albedo effect, it is more likely that what we're seeing is just a big long holdover from 2016, which we know was just an unusual collection of atmospheric events. And it is possible that the sea ice could recover, at least temporarily. If what we're seeing is down to this deep ocean warming, though, we know that that deep ocean warming is due to our greenhouse gas emissions, and we know that it's going to keep coming up warm for many, many decades, probably even centuries, so the sea ice isn't going to recover. So that question around where the heat's coming from is actually really pretty critical. And just to give you a teaser, this was from one of our postdoctoral students who actually submitted this paper. This plot is from a model experiment where Hannah Dawson artificially warmed up the deep ocean and ran the same model multiple times. And you can see that the spaghetti there, these are the observations. The red lines are what the model does when we warm up that deep ocean compared to what the model does when we don't. And if you notice the pattern of warming, which is very winter intensified, looks a lot like what we're observing, both in magnitude and the timing. So while we can't say anything definitive just yet, this is just a teaser, it's beginning to look pretty serious. But even if this is a blip, even if this is a surface warming, we should think about the future. So this plot here is from the recently published National Climate Risk Assessment, which has an appendix on the Antarctica and the Southern Ocean. And what we're looking here is Antarctic sea ice area as a function of global surface air temperature anomaly. Now, all those multiple grey lines, and I'm sorry they're a little faint, there's about 50 of them in there. No, yes, 50. And they're all from Australia's climate model. And basically they are projections of sea ice. The red dots are the observations that I've already shown you. And if we go past that 1.5 degree limit, which realistically we're already at, we can see that that loss of sea ice as the planet gets warmer does start ramping up. And remember the importance of that winter sea ice for that basal melt component of ice sheets, ice shelves, which leads to sea level rise, for those penguins, and for that pumping mechanism that helps absorb heat and carbon. So the future is a little worrying, and 2 degrees is really not a good choice for us to make. So I'm going to wrap things up there. And hopefully I've convinced you that Antarctic sea ice, whilst being a little ephemeral and a little thin, is a critical part of our global climate system. It's not just part of Antarctica, it is part of our planet. And whilst it was seemingly unaffected for many, many decades, had we but noticed there were indicators that a change was perhaps coming. Now, we don't quite know what the physical mechanism of change is, and that does have an impact on what we can say about whether humans are responsible for that recent collapse or not. Watch this space. However, we do need to acknowledge that the clock is ticking in terms of action on climate change, and if we really want to have a control on those effects, we've got to act very, very quickly. 2050 targets don't matter. 2035 targets are really the only thing that matters right now. Thank you very much.
Thank you, Dr. Will. Really appreciate you coming in. Does anybody have any questions?
You need some layman to ask a silly question. I'm asking, can we measure the heat emitted by the sun from year to year? Is it a constant?
So I'll just repeat the question for the recording.
Yeah.
The question was, can we measure the solar radiation emitted by the sun year on year?